several topics, and the first of them is a core topic to understand why the combination of renormalization group plus EFD is so useful, because we will discuss how the combination and the sums large logarithms, which is the technical outcome of the combination. So we have the following section. 5.3 the summing logarithms. So again, we work in 5 to the 4 theory with the M sparse, and we neglect the mass of the particle in the 5 to the 4 theory, and we look at large logarithms which can appear in a physical calculation. The relevant renormalization ingredients are the beta and gamma function. The beta function gives the running of the coupling, and we write it as a power series in the coupling constant. It starts with p to the second power, so p times a sum over L equal to N1 times the coefficient p per L times 2 to the L, and L stands for the loop order. At every loop order there is one additional power of the coupling, and at one loop order we have G0. And similarly, there is a gamma function which governs the running of the normalization. And it is simply given by a singular sum gamma L minus G to the L, so the running starts at order 2. Then let us look at some endpoint group function. Let's say T with n field operators is in general a function of the coupling and explicitly of the localization space. And as usual, we do not write physics arguments like energy, momenta, and so on. They exist, of course, as well. But depending on the green function at lowest order, the lowest order Feynman diagrams contain some number of vertices. For a 4.6-point function, like the non-inclusive diagram with a certain number of vertices. Therefore, at lowest order, we have some power t to the capital N. And n depends on the green function, but then at every additional loop order, there is one additional power of the coupling. So we get a sum L from 0 to infinity. To the L times some function and coefficient function L. Okay? So here the sum starts at 0, because the green function of course may have a 0 contribution, two-level contribution. The beta and gamma functions have no two-level contributions after epsilon is equal to 0. And so the dependence on the coupling is explicitly a power series. Therefore these coefficient functions can only depend on beta. And of course the coefficient functions will also depend on momenta energies of the physical process, but not on the coupling. Then, what do we know about the coefficient functions? At tree level, the coefficient function cannot depend on u, because u only enters via loops. Therefore, at tree level, u0 is a constant. Then at the higher order, the question is what is the mean dependency? And intuitively we have already discussed in the last lesson that the renormalization integration is not fulfilled at order by order, but it governs the relationship between different orders of calculation dependent, but the running of the coupling is that of one loop order, and the running of the one loop coupling is cancelled by the one loop independence of the V1. So there is always such a relation. Today we will analyze what is the implication of this particular relationship. So anyway, so this is okay, and there is now a statement which we are going to prove. The statement is that this TL of mu is a polynomial in LNU of order k. So this is like at one loop where we saw explicitly LNU first, never saw LNU square first, but that is representative for the general. Okay, and there is now a statement which we are going to prove. The statement is that this TL of mu is a polynomial in LNU of order n. So this is like at one loop where we saw explicitly LNU first, never saw LNU square first, but that is representative for the general case of all loop orders in the polynomial. So we can write it technically in the following way to make it explicit. TL of mu, the function of mu, is actually a sum of some index n from 0 to L of L, L times mu to the power n. That is how we can do this. And then we have made explicit and then of course, as I said before, there is always also a dependence on energies and momentum, and this coefficient here can still depend. What must happen in the end is that LNU will be accompanied with other logarithms of energies and momenta such that we always have that less dependence of energies. But anyway, we can now establish this statement on the mu dependence. And it technically simply follows from the fact that the renormalization group equation establishes that relationship between different orders in perturbation theory. So we will get some iteration or recursion formula which gives us the next order in terms of the
هناك أمر ما نجي نرجع مرة أخرى للجرين فانكشن، نجد أن العلاقة مع ميو تكون في الكوفيشنت، أي أنها ليست أصيلة في الجرين فانكشن، وهذا يعني له ما بعده، يعني له تفسير فيزيائي أنه الميو الذي ما يحصل للميو هو أنه لا تعبر عن الكتلة وتغيرات الكتلة في الفضاءات المختلفة تظهر في الكوفيشنت ولكن لا تظهر في الجرين. وهذا واضح لأنه الجرين فانكشن تعبر عن فضاء بين الكتلة وبين المادة. الكوفيشنت يعبر عن كتلة تتحرك في هذا الفضاء، كتلة أخرى غير الكتلة المسببة للجاذبية. فلا يمكن ندخل الكوفيشنت الخاص بالميو إلى الجرين فانكشن كأساس لها يعني في الباك بون أو في السبيس أو في الفضاء الصناعي الأبعاد. وإنما يعبر ما يعني ما يفعله الفضاء الصناعي الأبعاد لهذه الميو. وبالتالي يمكن أن نضيف أي كوفيشن آخر يمكن أن نضيف ويعبر عن الفيزياء الخاصة هذه الجسيمات. يعني مثلا تعالوا نقول مثلا يمكن أن نطبق الجرين فانكشن على الثقب الأسود ونرى ماذا يحدث للجسيمات الساقطة في الثقب الأسود. نرى أن كتلتها تضعف، نرى أن قوة كولوم تضعف، بالتالي يمكن نضع كوفيشن آخر يبين أن قوة كولوم تضعف، ونرى أن جاذبيتها أو القوة المسببة للجاذبية داخلها يضعف، ويمكن أن نضع كوفيشن وهكذا إلى أن نضع يعني مجموعة من الكوفيشنز تصف لنا الفضاء الداخلي للثقب الأسود. أيضا هذه الكوفيشنز يمكن نضعها لتصف الفضاء الداخلي للبروتون، ثم بعد ذلك لبداية الكون، وهي واحد طبعا بالمناسبة، واحد لأن الفضاء متصل، فيجب أن تكون الكوفيشنز كلها واحدة. ما يحدث داخل الثقب الأسود هو نفسه ما يحدث داخل البروتون، هو نفسه ما يحدث في بداية الكون. بالتالي يمكن نضيف أي كوفيشنز نحن نريده.
Yes, because at L equals 0 we have a new independent constant, that means here L equals 0. Then let us also assume as a reduction that it is 2 for previous orders 0 up to n minus 1, and then let us prove that from this we get and then we have a reduction. So under these two assumptions we get the following. We simply write down the renormalization group equation, and the renormalization group equation tells us that 0 is equal to the differential operator actually by the avenue partial derivative plus beta times y plus n times gamma. That differential operator acts on the green function, and the green function is this way, g to the n overall times a sum of l. Let's call it L prime now because L is fixed. That is the overall loop order we are considering. But here we have a sum over L prime from 0 to infinity in principle of the coefficient function L prime of the loop times g to the L prime. So that is our equation. And from this we want to establish our statement by plugging in that assume the statement is already true for prime which are smaller than L. And it comes from the fact that the beta and gamma function are of water. So simply let us look at the order n plus L. That is the next order that we need. The n function has already reached the number of trees. So that is the coupling. So let us isolate all the terms in the equation of that. Where do these terms come from? So here, the partial derivative with respect to everything simply acts on the coefficient functions which are independent of each other. Therefore, for this partial derivative, each term has some contributions. Only one term in the sum contributes, namely the one where gamma starts at equal to 1, so it also means the value of is 1, and so forward is 1. Therefore, if we act with this differential operator in combination with our d by dt plus n times gamma, we act on the sum, then which terms in the sum now contribute, right, from 0 to infinity, not all terms contribute. If the overall quantum of this power, and the differential operator is at least of order equal to 1. So we need here only terms where overall power is less than this. What does it mean for our index? L prime, so the sum L prime. Several values of L prime contribute. So 0 contributes, 1 might contribute, and so on. But only the terms between 0 and L minus 1. This power is always less than the power we want. Then of course we now know that here our induction hypothesis of lower order this already is a polynomial of the valid. What is then the result? Is it up to n minus 1? Powers are modified, but there is a polynomial. So it's a polynomial of minus 1. This here must also be a polynomial of first derivative is a polynomial of L minus 1. It's a polynomial of That's it. So this is the whole proof. At any order, any function in a quantum is a polynomial with LMU, and it is a polynomial of the corresponding. Very simple statement, but very powerful. So full control over the elements, and you see that the polynomials are actually related. So it is not only that we know that there is such a polynomial, but actually the proof tells us more. Here the proof tells us a lot more, namely the polynomial of the next order can actually be extracted from the polynomial at the previous order. You do not need to do calculations in order to get this. In fact, the polynomial is almost completely determined by the previous orders if you know the Wien gamma function. There is just one little detail which is not determined by the lower orders. Who can see the detail which is not determined? The constant. So the element-dependent part is not determined by lower orders, but the entire LMU dependence at higher order is determined by lower orders if you know the dependent part. So, for example, at 100, the LMU dependence can be constructed constructed if you know T-level and the P-type gamma functions. How many orders of the P-type gamma functions do we need in order to construct, for example, the one loop you want the LNU part? P-type gamma functions or also functions in order to construct the LNU part. Something I want to write down in the recipe, which orders you need for one particular purpose. So there are additional details maybe in the version formulas. If you only want the highest power, you have a new term for the power L minus 1 in this equation here. To meet this equation, we are at the order L, and this equation, the highest LNU term which can appear is power L minus 1. And in order to get the L minus 1 term, here we only determine the sum where L prime is equal to L minus 1, the highest power. We need everything else contains only lower powers of the group. Then if we are here already at the order L minus 1, then from the bracket we only need the 1. Therefore, in order to construct the highest power log, we only need R1 and gamma 1. Read backwards, it means that if you have the one loop beta and gamma functions, you can construct that all orders the highest term. That means the one loop beta and gamma functions if you positively sum up all logarithms of this loop. Let's make it explicit. So, for example, in this equation, get here, if you plug in this notation, the notation is that our functions L of u are now written with some coefficients. Then from left term, the derivative gives us power L times the coefficient L, L times the derivative of the log, and we can transfer the log into the terms on the right. We have one coefficients, and that acts onto the coefficient L minus 1, comma L minus 1. So that will come with the coupling C to the power N plus L minus 1. Then the derivative by dt acts on it, that gives us a coefficient N plus L minus 1 times the 1 coefficient. And then N times the gamma function. N times the 1 gamma 1 coefficient. That is exactly the term out of this equation, which is proportional to this power of the log. This is exactly a recursion formula. If you know the lower order coefficient of the highest log power, from this equation you get the highest. Transparent LA is given by PA minus 1 or PA minus 1 times the following fraction divided by A, and then this one minus beta 1 minus A plus A minus 1 minus A minus gamma 1. So that makes explicit that if you have p-level 0, then you could construct the one loop coefficient p11, then the two loop coefficient p3 power A, then from the following ingredients from the p-level 0 and gamma 1. The p-level is for your b function and the one loop beta and gamma functions, and then you can construct the index. And so on. You could derive similar recursive formulas for the sub-infinite operation, sub-infinite operation, and so on. The recursive formulas which you can work on the main point is you can get them, and anyway the renormalization group equation automatically determines all those definitions. I just want to make this as a table, maybe this last statement. Power A minus 1 at L order. So just from looking at the equation, what changes if you have one power of log less, then here in this term also one term of lower order contributes, but all the even lower terms will still not contribute, so you need one term more here. That means we need the one loop in order to get the next iteration. So in theory is then the following table. Let's say how does the contribution look like? At the free level, we simply have P0, which is constant, which doesn't even work. At the one loop level, you have P1, 0 plus P1, 1 times LW. At the two loop level, you have P2, 0 plus P2, 1 LW plus and so on. What is determined by what? Suppose you have done your t-level calculation of the green function, then what we have just discussed is that from t-level and the one loop gamma functions you get a leading log here. So you need beta 1 and gamma 1 in order to get the T11 coefficient. And with the same 1 loop beta and gamma functions, you also get this log term at the leading level and the leading log at the receiving level, and so on. So you automatically know what is determined by what. Suppose you have done your T-level calculation of the D function, then what we have just discussed means that from T-level and the 1 loop and gamma functions, you get the leading log here. So you need beta 1 and gamma 1 in order to get the T11 coefficient. And with the same 1 loop beta and gamma functions, you also get this leading log term at the unit level and the leading log at the unit level, and so on. So you automatically get all these leading logs at all loop orders if you only have these medians, T-level and 1 loop and 1 loop. So, however, how do you get sub-leading logarithm, the next leading logarithm, in 2 ways? First of all, from T0, if you multiply this differential operator with 2 and gamma coefficients, you immediately get from T0 the sub-leading log at the unit level. Beta 2 and gamma 2, they matter in order to give you a partial contribution to this sub-leading log. But also, if you have the 1 loop term here, the 1 loop term times the 1 loop term gamma function, you also get the sub-leading log. So here beta 1 and gamma 1 times the non-logarithmic 1 loop coefficient also contribute. So in order to get the sub-leading log, you need all ingredients. You need first of all not only T-level but an explicit 1 loop calculation, and you need the 1 loop calculation. But then of course it goes on. From here, this one, that's also and for example, in order to get the sub-leading logarithm at the unit level, of course, always come forward to
ألا ترون تشابه بما بين ما قلته هذا الدياجرام؟ أننا نحتاج إلى الحلقة التي قبلها لنتعرف على الحلقة الجديدة. طيب ماذا عن العكس؟ ماذا إذا كان الحلقة القديمة ولا الأوردر الليث أوردر لديها component of the higher order، وبالتالي نحن علينا أن نذهب إلى الهاي اوردر عشان نجيب الكومبوننت الخاص بالليث اوردر. ماذا عن هذا؟ هل هذا يمكن أم لا؟ إذا كان يمكن هذا يعني أن نظريتي صحيحة في هذا الموضوع.
So when you see that the renormalization group tells you the coefficients of all these logarithms. central large locations. And often this is appreciated as being sound. The term is not particularly fitting, but it will but we clearly now have this statement. This column here, which doesn't contain logarithms of mu, that is the only thing that cannot be predicted, and therefore this is the only thing that actually needs to be computed with one explicit LU calculations. And this is also where the problems of non-convergence come. Why is this particularly useful if you combine the normalization group and EFT? Because if you know that the theory you're working in has only one physical scale, like one physical energy scale which is relevant for your problem, then all the LMUs that we have now discussed must be accompanied with a single log of the single energy scale in the process. You immediately know that whenever you see LMU, you actually have LMU divided by the state of your process. So single scale theory is a theory where this knowledge of LMU becomes extremely useful for physical. When you have a single scale theory, if you have an EFT where you have integrated all the heavy particles of the process, that's therefore the computation is not easy. Any other questions? If not, then application of the renormalization group. And actually the remaining time today I would discuss a few, maybe 2 or 3 small indications how useful in applications are, but not useful in the sense of applications of ESP, but more useful in a general sense. And depending on time, we might do and then the next lectures we will of course come back to the combination and so for this further developments. but a very important application, namely pure PCB, strong interaction theory, the theory of quarks and gluons with SU brackets. Let us set the quark mass to 0. That means pure PCB corresponding to the idea that the quark masses will arise from electron theory, the theory of quarks and gluons with SU brackets. Let us set the quark mass to 0. Corresponding to the idea that the quark masses will arise from electronegativity radiating. So as long as you do not consider electroweak interactions, the quark mass are naturally 0, and you just have a pure massless theory which contains gluons and quarks and interact with electronegativity, which contains only dimension 4 operators. So in this theory, the Lagrangian contains no dimension 2 parameters. The only parameter which appears in the Lagrangian so when we know the theory is renormalization group, that means the theory actually does not depend on the value of the renormalized coupling only, but it depends on the value of this very bare coupling constant that we call also is specified. My choice is pure coupling and let's draw a picture. And the diagram is the mu square and the coupling. And here, without index, we have these trajectories. They look like this. They pose some low values is mu square, and at higher mu square they converge. So in this point of view, the theory is specified by specifying on which trajectory are we acting. So each value of dB corresponds to a different trajectory. So specifying the value of this. But now let us look at the graph, and there are two equivalent ways to specify on which trajectory we are. Either we can say the value of capital D, which is unphysical because it is also epsilon, and so on. But we could, for example, write the graph like this. And of course the natural thing would be to say we specify our theory by choosing a value of the renormalized coupling, but in order to specify the renormalized coupling we must now specify a value of mu at which we provide the value of we provide a reference scale, and that is reference scale specify the value T of 0, let's say, and then we specify by giving at the value, for example, 0, specified by choice of reference value. Okay, so that is not particularly surprising, but let us go on. Add a mu square and trajectories as before. And since they have this property that the trajectories approach 0 at large mu square and infinity at small mu square, it is clear that we can equivalently specify which trajectory are we on by fixing a reference value of the coupling constant and then specify what is the value of u at which we obtain this particular reference value of the coupling. So we would say u of some reference value g0. So we do not give a value, numerical value of coupling, but we provide a numerical value of u at which the coupling has a certain value, for example, coupling constant equal to 1 at either u equal 1 g and so on. So this is an equivalent way to specify which QCD are we actually getting of at some reference. Specify the numerical constants in your theory by specifying actually coupling constant, which is obvious, or specifying u. But what has now happened? Something very has happened, namely a dimensional transmutation. You have replaced the dimensionless parameter g in favor of a dimension full parameter. That has profound physical. Let's write it down. Parameter g in favor of parameter mu. And this exchange is called dimensional transmutation. But now we have discovered that specifying g is equivalent to specifying the full value of u. And what is the physical role of just specifies mass. Say u is 1 g or u is 2 g. Just defines what we mean by therefore, choosing different values of u do not change the physical. That means there is no parameter. There is just a choose the value of u. But that has no physics. That means that no physical result can depend on mu and what are physical results. The unit is choice of unit is always different. For example, the meter or the mass units or astronomical doesn't matter. The only thing that we can actually measure is dynamic investing ratios. The ratio between the unit interested divided by some length of the size of the proton compared to your length of how many protons fit your matrix. So you have two physical objects, both described by the same theory, and it's one relation. And therefore physical results are always measureless ratios. They cannot depend on your independent of your. Therefore, PCB has zero free parameters. That is a nice statement. There are dimension-full fundamental parameters in the standard model. For example, expectation value, and there are dimensionless ratios of parameters in the standard model. But that is not very important because the standard model has already some parameters and therefore the value of mu some remarks also on the standard model anyhow, because the dimensional transmutation and qualification is also of interest to the application. But first with the definition here, we have this simple statement that the parameter, and the fact that we have a parameter free field is really a quantity thing. In the classical limit of 2C, there is no such thing. Because at the classical limit, there are no beta functions, there are no running couplings, so there is only one result. So the vector is really flat on the horizontal lines. Therefore, the classical limit is work, and you would need to specify the numerical value of the gauge coupling, and that would determine the nature of the classical solutions to the equations of motions in QCD. But this step would be impossible. You could not grade the gauge coupling on the classical level in favor of some dimensional parameter, and therefore say it is equivalent to a choice of the classical, which is not equivalent to a choice of. So classical QCD is one thing, but QCD at the quantum level has zero. Outcome of the quantum, which makes it even more unclear. Definitely not the horizontal lines. And therefore, classically this will work, and you would need to specify the numerical value of the gauge coupling, and that would determine the nature of the classical solutions to the equations of motions in QCD. But this step would be impossible. You could not grade the gauge coupling on the classical level in favor of some dimensional parameter, and therefore say it is equivalent to a choice of the classical, which is not the classical is one. The quantum level has zero. So that is the outcome of the quantum. Which makes it even more unclear. Just reduces the amount of this whole QCD viewed fully as a quantum theory with all of these quantum effects is a parameter free field at this quantum level. Let us now look at QCD embedded in the standard model. So here the standard model defines the mass scale. For example, Higgs vacuum expectation value, or the mass of the Z boson, which is easier or unambiguous to measure. And then going through these steps, we could accurately say that QCD has one physical parameter, a coupling constant, at this value of mu equal to Z. Then the role of dimensional transmutation. It is basically an interesting calculation that you can do. G of below is fixed at some large scale. To mz, and numerically we would get square of z divided by 4 pi, which is alpha, for the strong coupling constant. It is known and it is measured to be around 0.1. So it is a small quantity. But actually the gauge coupling G of mz is approximately 1. When V squared divided by 4 pi is approximately 0. So then there is this Landau pole of the trajectories at small energies, and we can calculate its value. So the relationship is 1 over 3 square at mz minus 1 over 3 square at the Landau pole, which is 0, is equal to beta 1 times ln lambda square divided by rho square, where lambda is the value of this Landau pole. And then you get an exponential solution for this. Lambda square is equal to square is z square times the exponential of 1 over So here we have a formula that we have already seen last lecture. A non-perturbative formula is exponential of 1 over a coupling square, because it essentially singularity at coupling equal to 0, so it's a non-perturbative expression. And if we plot it, it looks somewhat like this. So here we have the energy scale mz, here we have our new axis, and at some very small energy looks approximately like that. And the point is now that our fundamental energy scale of the full theory is a very large value at z, like almost 100 dB. And this non-perturbative expression predicts that it basically generates some complicated non-perturbative dynamics, which produces dynamically a new energy scale at which we get confinement of non-perturbative bound state phenomena. And the energy scale is exponentially suppressed by this non-perturbative. We have a obviously very large separation of the two scales, and the formula is non-perturbative, and it corresponds to the energy generation of these mass scales of bound states. Physics happens here, and of course also here in the region where the coupling becomes very large, propagation theory is not trustworthy anymore, so probably the true trajectory of the running coupling is different from the plot. But it is clear that non-perturbative physics sets in and takes place in the dynamic electromagnetic exponential. So that is very nice. So this is an equivalent use of the renormalization group equation, which is related to the phenomenon. And so also this is a role model. If you have some small mass scale which you are interested in, you might want to explain dynamically using some fundamental theory where this mass scale comes from. And here basically gives you one example how it can work. Fundamentally, you have the interactions which have a expected expectation value. Then you as beta functions gives you the explanation why at some exponentially smaller energy scale bound states. You have the explanation. But current open questions in physics are, for example, where does the vacuum expectation value of things come from? Is there some dynamical origin of the scale of the Z mass, and the scale of the X mass, and the scale of the Mexican shape of the X potential? And for this we do not have an what is now coming as a reformulation of the Renormalization equation. But the way of thinking behind it is a little bit different. I will explain you at the end what is the different way. Anyway, let us start with the following observation, that there are two kinds of energy scales in a theory. The first kind of energy scale is what we have now mostly been discussing, namely mu and mass parameters, which are full parameters of the Lagrangian. So these energy scales are part of the definition of the field, part of the definition of Feynman diagrams, and they are fixed once and for all. And all of these parameters are constants of nature, basically. There will be no change on the other hand, there are of course physical energy scales like momenta, kinetic energies of particles, and they are experimentally accessible. Energies of particles. Different depending on the process we are using. We are not only momenta and energies, but it could also go to position space, and then there are things like position, time, and so on, which are also dynamic. Focus on the first kind, but now let us focus on the second kind of dimensional quantities, namely we would like to work on a fixed field and then discuss physics. And physics means that we discuss how observables depend on physical energy or length or time scales when the field, however, is not fixed. That is actually the natural. So in particular, we now look at the scale transform. The scale transformation is a transformation which scales up and down all the energy and length and time scales of your physical observables. In other words, it scales up or down those experimentally accessible quantities. So quantities, we take any 4 vector, it's mu, minus 1 times x mu. Becomes p times p mu. P is a real parameter, and for dimensional reasons x and p of course scale in the opposite way. And also field operators in the Lagrangian, they also scale up or down according to the dimensionality of the field operators. So they scale like t phi I, where d phi I is the dimensionality of the field operator. Let us ask how this change under such a state transformation. First question, are observables scale invariant? Is physics scale invariant, for example, in nature, in real life, in our reality here in the lecture hall, for example? Is physics invariant under such a state transformation? right, but you still have some impact over somehow the molecules there are some fixed sizes. Where do these fixed sizes of molecules come from? They come from some fixed length scale that apparently exists in the literature as a fixed length scale corresponding to the radius of molecules. This is a fundamental length scale. write all of that down. Or in other words, let's discuss it in detail. First of all, this is a scale transformation. And now step by step, discuss to what extent something is invariant. And let us begin with the classical theory, where quantum effects are ignored. So for example, QCD with work mass equal to 0 again. So in QCD with 0 work masses, the Lagrangian classical contains no dimensional parameter. And classical unit, there are no quantum effects. apply this scale transform parameter 2. Then what happens is that every term in the Lagrangian behaves as follows. Every term in the Lagrangian contains an operator consisting of the operators in the derivatives. Lagrangian becomes itself times the positions having the opposite way, so whatever stays there to the minus 4, therefore when this invariance is broken, you would not have such an invariance if there would be an explicit mass term, because then you would not scale up and down the mass, but only the two operators in the derivatives. Then such a term with the mass would, for example, scale with the and then would be come out the explicit mass term would be an explicit scale. But let's working in the scale invariant classical field. Our assumption was no such master, therefore we have scale invariance of the following situation of physical quantities. Section, for example, or any quantity sigma depends on some set of momenta which has a certain sigma mass some power capital N. As follows: sigma is a plus times the momenta that is the simple Now, in order to compare this very simple sum over all momentum components of sigma, and this is simply n times sigma. So we get the following equation: the sum over all momenta is n space, and that subtract -4 pi plus 4. Here this +4 comes from delta function of the sum of all decoupling momenta, which always arises as a byproduct of Fourier transformation into momentum space for all So, for that, we know immediately that the field statement will be the following. The green function has the following scaling behavior. Now we need to take into account that it depends on picture momentum and on all the variables that we had considered before. So the green function depends on physical momentum, it depends on the coupling constant, it depends on the mass parameter, which is the density, and it depends on the representation scale, which is the Yes, but for this trivial analysis, we have the table, so this is not it. That is because here we are scaling up and down. Since we scale up and down everything with this dimension
طبعا سمعنا هذا الكلام انه على المستوى الكمي السكيلينج انفاريانس يحصل له بريكين، وبالتالي تخرج الأجسام ذات تخرج الجزيئات ذات شكل معين متناسبة مع هذه الأرقام أو هذه المتغيرات، اللي هو 2 مضروب في بارشل على بارشل لين إن تربيع زائد بارشل على بارشل لين ميو لين إن زائد لين ميو. هذان الحدان هما مسؤولان عن كسر التناظر الانفاريانس سكيلينج انفاريانس. بالتالي هذان الحدان هو ليس صفرا، وإنما يعبران عن هذا النوع من الكسر بطريقة أو بأخرى، يعبران عن هذا النوع من الكسر في الانفاريانس سكيلينج انفاريانس. وهذا طبعا له تأثير ناتج من ماذا؟ التأثير ناتج عن أن الكوبرينك لا يصل إلى لا نهاية. كوبرينك كونستانت لا يمكن أن يصل إلى لا نهاية، لأنه هو يتفاعل ويزيد مع الميو في الكيو اي دي، والكيو سي دي يزيد مع الميو إلى أن تأتي المرحلة التي يسيطر فيها الجلونز. فنجد أن في المرحلة التي يسيطر فيها الجلونز تنقص الميو لكن تزيد الطاقة، تنقص الام الكتلة لكن تزيد الطاقة. وهذا ما يحصل البريكن يحصل عندها البريكن اوف انفاريانس اوف سكيلينج. يعني أو هذه النقطة التي يحصل فيها نقطة الانقلاب، حيث أنه الام لا يمكن تتضخم إلى ما لا نهاية. يأتي مرحلة أن الفضاء يفعل آلياته بحيث أن الام لا يتضخم، وهنا نجد أن ام تنقص وتزيد الطاقة حسب النسبية الخاصة، لأن الفضاء ينظر إلى الام باعتبار طاقة، فهو ليست لديه مشكلة أن الطاقة زادت ما دام هنالك، أو الطاقة ثابتة ما دام هناك عنصر آخر جعلها ثابتة. هذا ما يراه الفضاء صناعي بعض، أن الطاقة يجب أن تكون ثابتة وأقل من التهديد له، وبالتالي إذا زادت الطاقة الفضاء صناعي بعض سيفعل شيئا آخر يجعل الطاقة تنقص، يجعلها ثابتة، سواء كان بسرعة الضوء أو بالام الكتلة.
observe this phase, this will change from a electrical state to the other side. When you observe this,
that should be sufficient for today. And next week